In this lecture, we're going to discuss about the linear perceptron algorithm. Specifically, we're going to discuss an example and the way we can represent the linear perceptron algorithm. And we're further going to describe some details on how we can learn the parameters of the linear perceptron. So let's assume this example in which we would like to decide whether we will approve or deny credit for a person based on some of their attributes, including, for example, their salary, whether they have a debt, or their years in residence. So what linear perceptron does is that it tries to solve this binary classification task by drawing a line if we have a two-dimensional space or a hyperplane in the case of more dimensions. And it tries to draw this hyperplane in such a way that as many samples as possible from one class go on one side of the hyperplane, and as many samples as possible from the other class go to the other side of the hyperplane. And you have probably seen so far that we have discussed that we are discussing a binary classification example. However, this can be generalized in a multi-class classification example, which will be presented at the end of these slides. So in this specific case, we have our two-dimensional space, which is represented by the first feature, which is a person's salary, and the second feature, which is a person's debt. These blue and orange samples represent people that got denied or got approved credit respectively. And our goal, as far as the linear perceptron is concerned, is to draw a decision boundary that is being represented by this linear line. And that decision boundary segments the space into positive samples and negative samples. So in the next few slides, we are going to see how to mathematically represent this line, how to also mathematically represent the decision of whether samples are on the right side or on the left side of the line, and then how to achieve our algorithm so that it can learn what is the optimal line to draw to achieve the best classification results. So let's assume that we have an input vector x, which belongs to d different dimensions, meaning that it has d input features. If we were to think about this credit score application problem, we would most probably assign each of the attributes a certain weight. So for example, if we had a person's salary and a person's money owed in debt, we would assign some weights to each of these two properties. And these weights here are being represented by the parameters wi, and we have d different weights, as many as the number of features. If our features belong to the same range, the weights convey the importance of each of these features. So intuitively, we would approve one's credit if the linear combination of our features multiplied by a certain weight is greater than a threshold. And we would deny one credit if the opposite condition holds. So the question here is how to choose the importance of the weights, and also how to write these expressions in a way that they can be translated into this mindset of vector multiplication, and into this specific problem of drawing a decision boundary via a line or a hyperplane. So going to our original equation that examines whether the linear combination of the attributes of our problem multiplied by a set of weights is greater or equal to the threshold, we can actually rewrite this expression as basically the linear combination of our attributes plus a bias term W0. And this bias term essentially represents the inverse version of the threshold. So after we're done with this, we understand that if this whole expression here is greater than 0, then it means that this condition will be met. Otherwise, if this expression is less than 0, then the denied condition will be met. So plus or minus 0 now can be represented by this sign notation. And this will be actually the final expression for our classification decision. Now, instead of having this expression in an algebraic notation, we can very easily write this in a vector multiplication notation. And the reason why we're doing this, as you can see this expression here, is because this vector multiplication is computationally much easier to handle by our computer. And also when we write our code is much more clean and it doesn't need so many lines of code. And so many for loops. So this expression here entails this weight vector, and this weight vector has the weights of all the attributes of our problem, and in the beginning it also has the bias term, which again represents the inverse of the threshold in the original equation. And also the second vector, which represents our samples, has all the attributes in the second all the way to the last position, and its first position represents this number 1. And the reason for that is that when W and X are being multiplied together, this one will be multiplied by the bias term, and essentially this will cause our linear combination of attributes to be added to this bias term. So what we would like to do is, at the end of the day, we would like to see whether this notation here, this notation of h of x here, is greater or equal to 0. And this would signify that our input sample x will be classified either as the positive or as the negative class. This slide here actually summarizes exactly this representation. If W transpose X is greater than 0, it would mean that our sample X belongs to class 1. Otherwise, it would mean that our sample X belongs to class -1. So how actually can we transform this equation into a visual representation where we have a line or a hyperplane? It only takes for us to remember that the vector that is perpendicular to a line, especially if we have, in this case, this two-dimensional line, can be written in this notation here. So essentially, if we have a line W1 x1 plus W2 x2 plus W0, then the vector which is perpendicular to this line actually contains the first two weights of this line. And there is a separate proof for that that will be provided in a supplementary handout. So what we would like to do now is that, thinking about that, we would like to find the line W or the hyperplane that is represented by the vector W that separates the data. So one idea, if we have a binary classification example in this case, is to start with a random line. So let's say that we have our positive and our negative samples here, which are being represented by the red and the blue colors respectively. As we can assume that randomly we draw this line, which is represented by this black color. And based on this line, some of the samples are classified correctly and some of the samples are classified incorrectly. Specifically, we see that if we assume that the red samples belong to the positive class, then these two red samples are correctly classified and these two are incorrectly classified. And similarly, this blue sample here is incorrectly classified. So let's now see how, after we have performed this random initialization of our decision boundary, how we can actually correct our decision boundary in order to yield a classification of our training samples which can classify our training samples in a correct way as much as possible. So in this specific example, we are going to assume only 3 samples, x1, x2, and x3, that are also being shown in this 2-dimensional space. And we will assume also that these belong only to the same class, essentially to the class y equals 1. So this green line on the left figure here represents the initialization of our decision boundary. We can see that that samples x2 and x3 belong to the positive class and are on the right side of the decision boundary. Therefore, they are correctly classified by this line. However, sample x1 is on the left side of the decision boundary while it belongs to class 1. Therefore, it is incorrectly classified. And here we also have a convention that whatever is on the right side of the decision boundary, we will say that it will belong to class 1, and whatever is on the left side of the decision boundary, we will say that it belongs to class -1. Here, we also see that this green line is being represented also by this vector W0, and the direction of this vector indicates the direction of whatever it is on the right side of the line or on the left side of the line. Specifically, since W0 now is pointed towards the right side of the line, we know that vectors W0, X2, and X3 are in the same direction. Therefore, X2 and X3 are correctly classified, while sample x1 is incorrectly classified. So how can we adjust the line in order to make sample x1 also correctly classified? We can actually add sample x1 to the vector that represents our initial line W0. And by doing so, as we can see here, so when we add x1 to W0, then we can get a new vector W1, which also has this perpendicular green line to it. Now, what we see is that this perpendicular green line can correctly classify samples x1 and x2, since samples x1 and x2 are on the right side of the line, but incorrectly classifies sample x3. Therefore, we need to adjust the line which is represented by vector W1 in order to also be able to correctly classify sample x3. We will do exactly the same thing. We will add sample x3 on vector W1, and by doing so, we get vector W2. Now we can also see this green line here, which is perpendicular to vector W2. We can then evaluate this green line in terms of how many samples it correctly classifies. And we see that all our 3 samples, x1 and x2 and x3, lie on the right side of this line. Therefore, our vector W2 classifies all our 3 samples correctly. If that was not the case, then we would pick a sample that is incorrectly classified from W2, and we would perform the same iterative procedure. So we have seen so far a very simple iterative method that relies on incrementally learning our weight that corresponds, that is perpendicular to our line. And this weight is being incrementally learned or based on a single sample at a time. So if we were to write this in a more formal way in a pseudocode, we will first randomly initialize our line, or the vector that is perpendicular to our line, W0. And after that, for as many iterations as needed, we would identify which of our samples from x1 through xn are misclassified. After we identify our misclassified samples, we can randomly pick one misclassified sample. Now, if our misclassified sample belongs to the positive class, what we need to do is that we need to update the weight such that the next weight has the misclassified sample on the right side of the line. And this is being represented by a sum operation. However, if our sample belongs to the negative class, then we need to subtract this sample from the weight such that the weight, basically such as the misclassified sample, eventually can lie on the left side of the line. And this is exactly what this equation represents. If our misclassified sample XS is labeled on the positive class, then YS will be 1. Therefore, in order to adjust the line, we will add sample XS to our previous weight W of T. However, if XS belongs to class -1, then YS will be -1. Therefore, we will subtract XS from WT. Again, by doing so, what we make happen is that if our sample belongs to the positive class and is misclassified, therefore it lies on the left side of the line, we will make our sample with this adjustment to eventually lie on the right side of the line. And vice versa, if our sample is on the negative class and mistakenly lies on the right side of the line, by subtracting our sample from our weight vector, we will make it lie on the left side of the line. So as you can see here, we have this T, which represents time and essentially represents as many updates as we do to our weight vector. We can do as many updates as we want, and the final number of updates can be determined either by a predefined iteration number, or we can do as many updates as long as the sample the weight WT does not change much, or if we have a linearly separable case of data, we can do as many updates as we can so that we correctly classify all our samples. Now, a small caveat in this is that our vectors W might not always be normalized. And for this, it might be the case that when we add or subtract our misclassified sample XS, we can disproportionately modify the vector W, and actually we can get a vector W that might have nothing to do with the one from the previous iteration. In order to mitigate that and mitigate this large impact that a misclassified sample XS can have on the weight update, we can actually have a hyperparameter, which we call a learning rate. So this hyperparameter alpha controls how much our weight W will be changed, will be modified based on this misclassified sample. If our learning rate is very large, then our misclassified sample will have a large impact on the update. And if our learning rate is close to 0 or very small, then this misclassified sample will not influence the update much. Now, this learning rate is a very typical hyperparameter that is being used in many machine learning algorithms and depends on the data and on the problem. Sometimes, as a common practice, we keep a higher learning rate in the beginning of the iterative process, and then this learning rate is decreased as the time eventually goes by, which is what is being depicted here with this example. So the learning rate depends on the number on the current iteration T. The higher the iteration, the lower the learning rate. Now, as an issue arises from this linear perceptron algorithm in terms of its algorithmic convergence. So the rule update that we have right now considers one training sample at a time, which is being randomly picked from the misclassified samples of our data. This means that we have pretty much no control of whether our algorithm will converge eventually, because there might be a training sample that might actually destroy the classification of all the other samples, and then essentially we'll have to start from scratch. So if we have a linearly separable training set, then our algorithm will eventually converge, just because after some finite steps, our algorithm is guaranteed to arrive to a correct solution. However, if our data is not linearly separable, then eventually our algorithm will not be able to classify all the samples correctly, and potentially we would need some non-linear classifiers in order to successfully conduct this classification task. And the potential way in order to achieve this is by combining multiple perceptrons that can fit our data in a better way, which is something which is the foundation behind the neural networks, which we are going to see in our next classes. So as we have understood so far, the perceptron learning algorithm is a local and greedy algorithm. It is a local algorithm because it performs local updates based on a randomly selected misclassified sample at each step. And it is a greedy algorithm because every time it looks for a current misclassified sample. Because of this, our PLA can have an exponentially large number of updates. And in this case, we also provide an example of two samples. Here, this is one sample which is being represented by this vector here, and another sample which is represented by another vector here. So if these two samples are almost anti-parallel with each other and belong to the same class, then the linear perceptron will actually have a very hard time in finding a line that can separate between the two, especially if the learning rate is high. Because whenever the learning rate is high, and let's say we have this misclassified sample, then the linear line will be primarily adjusted to meet the classification rule for this sample. And then in order for the line to be adjusted for the other sample, which belongs to the same class, again, it will have to shift pretty much 180 degrees. So there is a distinction here between parametric and non-parametric models, as we had discussed in our previous video about the k-nearest neighbor. So we had said that k-nearest neighbors are non-parametric models just because the decision-making process does not assume any structure about the data space. However, the decision-making process of a linear perceptron pretty much assumes a linear structure about the data space and assumes that we can have a linear separable boundary that classifies our samples between the two classes. And this linear structure is being represented by a line or a hyperplane, or by the weight W that we have seen. So the weight W is actually the parameter of our parametric linear perceptron algorithm, and this weight is being learned from the training data. This is in contrast to the hyperparameters, for example, the learning rate alpha that we saw, that is being predetermined before we actually start the learning process. So now, after we have actually explained a little bit the binary case of the linear perceptron, we can actually extend this to the multi-class classification. And the way we do that is that we can introduce as many weights to the multi-class classification example as the classes that we have. In this specific question that will prime us for the multi-class classification example for the linear perceptron, we can assume that we have this two-dimensional data space that includes three classes, which are being represented by our three colors here. We can also assume that we have three classification boundaries that are represented by three lines, and these correspond to three different vectors, W1, W2, and W3. So we also need to pay attention to the directionality of the weights. Again, as a reminder, if the direction of the weight points out to the positive class that corresponds, that is being determined by the corresponding line. So if we have this vector W2 here, which is being pointed to pretty much the upper direction, it means that whatever sample is on the same direction as W2 will belong to class 1. Therefore, the inner product of this sample with W2 will be positive. And whatever sample is on the opposite direction will be represented by the negative class. Therefore, its inner product with W2 will be negative. So we would like to see which of these equations hold here. And we can see here that pretty much all the samples, or basically all our samples X1, X2, and X3 that belong to classes C1, C2, and C3 are in the same direction as the direction that the vector of the corresponding line points to. Therefore, the correct answer here is A. So basically, from all the blue samples here, X1 that belong to class C1, if we take their inner product with W1, this inner product will be positive because these blue samples lie on the same side of the line as the direction that W1 points to. Similarly, all these pink samples that belong to class C2, these samples X2, if they are being multiplied by W2, this inner product is positive, and the same for samples X3. So this is actually the foundation for the multi-class linear perceptron. According to this, the representation is that once we have once we have a D-dimensional input space, our output now, instead of being a positive and a negative class, corresponds to k different classes. And our decision rule is being taken such that we assign for each sample X, we assign it to the class that has the largest signed distance for this sample X and this class. And this largest signed distance is being represented by its inner product with each of these lines that correspond to the k classes. So if we have k classes and these are being represented by a vector wk, their inner product, this w transpose x, represents the signed distance of sample x to the corresponding class k. Now we would like our sample x to be as far as possible from the boundary of that class, because in this way we will know that our sample X, first of all, is on the right side of the boundary, and it is as far as possible from the boundary, of the corresponding class. Therefore, our decision-making rule will be that we will assign sample X to the class that corresponds to the largest inner product between X and vector wk. So after we have done that, we understand that we have, instead of now having only one hyperplane, we have k different hyperplanes, each of which is being represented by a vector wk. Now the question is, how do we learn these hyperplanes? We can actually introduce a cost function. And this cost function here that we see evaluates the difference between the signed distance of each sample from its currently assigned class and the distance of the sample from the labeled class. So in this equation here, this maximum of WK transpose XN represents what is the assigned class, the distance of the boundary of the assigned class of sample Xn, meaning if our current decision boundaries are being represented by vectors Wk, we are going to find which of the classes has the largest signed distance, and this is the class in which vector Xn, sample Xn, is being assigned. Now, we would like this class to be as close as possible to the actual class of sample Xn. And this actual class here is being represented by our label Yn. So since we are comparing the distance of sample Xn from the assigned class and the distance of sample Xn from its true class, we would like this distance to be as low as possible. And we learn this distance for all our training samples Xn. That is why we have this sum here that ranges between 1 and n. And we minimize this whole sum with respect to all the weights W that correspond to each of the hyperplanes of each of our K classes. This problem can be either solved similarly to the two-class perceptron, essentially via an iterative process that shifts the hyperplanes based on the misclassified samples, or there is also an alternative to that via approximating this cost function with the cost function for which we can actually compute a first-order derivative, and therefore we can apply gradient descent in order to find the proximal solution. So to summarize, we learned about the linear perceptron, which is a very simple learning algorithm that assumes a hyperplane which separates our multi-dimensional space into two classes. We said that whatever is on one side of the hyperplane will belong to the positive class, and whatever is on the other side of the hyperplane will belong to the negative class. We saw an iterative greedy algorithm that adjusts the hyperplane according to the misclassified samples. We also discussed that this greedy algorithm is guaranteed to converge if our training samples are linearly separable, but obviously we cannot find a solution with this linear algorithm for non-linearly separable training data. And finally, we also saw an extension of the binary classification case into a multi-class perceptron, for which instead of using one decision boundary, we use as many decision boundaries as the number of classes.